Okay, video number 4, and at this point we're moving from a simple model of a one-cell model towards directly a three-cell model. There is no two-cell model happening, so we move directly to the most complete and complex one. At this point, we will assume that our planet is spinning, rotating, which is of course what's happening, and then we kind of still have the other assumption. But this will lead to, in fact, a difference in terms of the convection. It doesn't blow directly from the equator towards the pole, but it's breaking down into three cells models that will be blowing winds into different cell units. So a cell is, in fact, as you can see right here, a system of high and low pressure that will be distributed between the 0 and 30 degrees latitude, between the 30 and the 60 degrees latitude, and between the 60 and the 90 degrees latitude. This will give some different wind patterns in each of those cells. The first cell between 0 and 30 degrees latitude is what we call the Hadley cell. It's where we observe the convection happening at the equator with a lot of clouds happening and precipitation around the equator, and the sinking of dry air around the 30 degrees latitude, which explain why we tend to observe a lot of desertic zone on the 30 degrees latitude, what's also called the horse latitude. And then from the 30 to 60 degrees latitude, you have a high pressure system to a low pressure system on the 60, with some convection happening and some rain, but less than in the equator, happening at the 60 degrees latitude. I forgot to mention that the first cell is called the Hadley cell, the second one is called the Ferrel cell, and then the third one that links, in fact, the 60 to the 90 degrees is a polar cell with cold and dry air that's in fact sinking onto a high pressure system on the polar region, which explains also why there is not too much precipitation. With that type of model, we come towards something that is more realistic to what we can observe with the some three patterns of wind happening. We have a wind that blows from the northeast toward the southwest here in between the 30 and the 0 degrees latitude, which is what we're calling the trade wind or the easterlies. Then between the 30 degrees to the 60 degrees, we have what we call the westerlies, wind blowing from the southwest toward the northeast, and this is the type of wind we observe here in North America. And finally, in the pole region, we're back to some easterlies from the northeast toward the southwest, called the polar easterlies. And so this is kind of the model that is perfect. As soon as we start adding a little bit more feature that we can observe, this is giving us a more realistic view, which is in fact kind of explaining better the type of climate we do observe. On this one, mostly what we had was the continent. We had the land in two pictures, and we see a redistribution a little bit of those cells and the formation of high pressure and low pressure system. But again, the wind system is very much the same. So we do have that Hadley cell right here, the Ferrel cell and the polar cells, with the trade winds are called easterlies, the westerlies and the polar easterlies happening right there, providing us a climate, a model of the climate that is closer to what we are used to observe. If we go quickly into each cells, we can quickly provide some description about it. The Hadley cell is where we observe the trade winds, also called easterlies. Both of them are fine. And those are winds coming from the northwest blowing towards, moving from the northwest toward the southwest, okay? In the southern hemisphere, they are just symmetric, so they're blown from the southeast to the northwest. They usually, those winds tend to be stronger during winter time because of the higher difference in temperature. This is one thing that we tend to observe, stronger wind happening during winter time. Then we're moving toward the Ferrel cell. At this point, this is a cell in which North America, the US, is inside, and the wind that's mostly dominated the Ferrel cell is what we call the westerlies, moving from the southwest towards the northeast. Oops, right here, my bad, right there. Those winds, I forgot to mention, I mean, all of those those winds are impacted by Coriolis. Ideally, the wind would be blowing this ways, but because of Coriolis, you're moving toward the right from the motion, from the direction. And so this is why we observe winds blowing like that in those cells, okay? Then the polar cells, mostly we're back to easterlies, what we call the polar easterlies, and the winds moving from the northeast toward the southwest. And so this is the coldest region and driest region of the world because of all the sinking toward the high pressure system that we observe of the poles. So at this point, as I mentioned, we came to a more realistic model as we add the landmass distribution, the ground, the continent on the picture. And what we can observe is that over the year, the convection happening at the equator is in fact slightly shifting. It doesn't exactly happen always at the equator. So we do have, this is a representation of the Earth, but on a cross section where we do have the South Pole right here, the North Pole right there. We have the equator, 60 degrees, 30 degrees south, 30 degrees, 60 degrees north, okay? With the Hadley cell right here, the Ferrel cell, and the polar cell. Ideally, we would think that we do have a perfect convection happening at the equator, but this change from season. The convection at the equator, what we call the ITCZ, we'll just talk about this in just a bit. For intertropical convergence zone, this ITCZ moved. As you see, during summertime, the convection happened more toward the northern hemisphere. During wintertime, the convection happened more toward the southern hemisphere, which is logical. It's following the summer season. So what we observe during January, when it's summer in the southern hemisphere, this convection cell tend to happen in the southern hemisphere, where it's warmer. During summertime, where it's warmer in the northern hemisphere, this convection cell, this ITCZ, move toward the northern hemisphere. So there is a motion happening. And what we can observe too is that the polar region, the polar cell, tend to expand during the season. We have an expansion of the polar cell, the North Polar cells during winter time, which is when it's colder. Meanwhile, we have an expansion of this polar cell in the south when it's winter in the southern hemisphere, so during our June period. As a result, you have everything summarized in this video.
Wind patterns. Wind directions vary from place to place on Earth's surface. The equatorial region receives more direct solar heating than the poles. The warm surface air, including evaporated moisture, becomes less dense than the surrounding air and rises. The initially warm, moist air mass cools as it moves higher in the atmosphere, and the water vapor condenses to form clouds and rain. This means that the originally warm, moist, low-density air is now both cooler and drier, which increases its density. The denser, cooler, and drier air sinks back to the surface at latitudes of about 30 degrees north and south. Air pressure measured at the surface is lower where air rises and is higher where air descends toward the surface. In general terms, then, air rises from a low-pressure belt surrounding Earth at the equator, and then descends to form high-pressure belts at subtropical latitudes, and then flows both northward and southward back toward the equator. The next step to producing realistic global wind patterns is to add the effect of Earth's rotation. Rotation causes all objects that move over Earth's surface or through the atmosphere to experience a horizontal drift called the Coriolis effect. The Coriolis effect shifts objects to the right of their initial path in the northern hemisphere and to the left in the southern hemisphere. The red arrows show the Coriolis deflections that produce the prevailing wind patterns on Earth's surface. Air moving southward from the northern hemisphere subtropical high-pressure zone is deflected to the right toward the west to produce northeasterly trade winds, whereas air moving northward from the high-pressure belt is deflected to produce westerly winds. The circulation between the equator and middle latitudes, therefore, includes the trade wind belts, where winds come out of the east, and the mid-latitude westerlies, where wind blows from the west. Cold, dry air descends near the north and south poles and moves toward the middle latitudes. These air masses are also deflected by the Coriolis effect to form belts of polar easterly winds surrounding polar high-pressure zones. Air masses moving away from the polar regions collide with air masses moving toward the poles and away from the subtropical high-pressure zones. The warmer subtropical air rises over the colder air, causing low-pressure cells and storm fronts.